Okay, good afternoon, class. Thank you once again for joining PHS 104. We are in week 8, and we will be discussing today dealing with waves and sounds. Okay, so we are in chapter 6, and we will be talking about waves and sound this week, which is week 8 of in our semester. So when we talk about waves, waves come in many shapes and forms. Right? While all waves typically share some of the basic characteristic properties and their behaviors, what we can say is that they can be distinguished though, based on some of the observations. For instance, when we look at what is known as a mechanical wave, right? This is a mechanical wave. It typically propagates energy outward from any kind of disturbance. Okay, you can see here someone throws a rock inside the water, and the ripples typically have that input has an output effect. It gives you this ripple effect. Okay, so that mechanical input has given you something physical that you can identify with. Okay, so also keep in mind that waves typically they generally transfer energy. Let me change colors here. They transfer energy and not matter. Okay, through a variety of mediums. And your mediums are typically we talk about the matters of life, or the different forms of matter. You have your solid, okay? You have your liquid, and you have your gaseous state, or gases. Okay, so these two pretty much are considered to be a fluid. Okay, so fluid can either be a liquid or a gas. But these are some of the mediums in which waves can travel. Also, wave can travel through vacuum as a form of light waves, which we'll talk about as you move forward. Okay, so here's an example of a mechanical wave that's typically propagating the wave outwardly. Right, you can see an explosion pretty much. Right, you can typically feel that effect. Another property of wave may be in the form of a periodic wave. Okay, playing a guitar string. Okay, so always keep in mind that these waves are nothing more than just um, a way of energy being propagated outwardly. Okay, and they use different mediums to do that. So when we talk about our mechanical waves, there are typically various types, but in particular we'll talk about the longitudinal wave. Okay, so our longitudinal wave typically it differs, of course, from our transverse, but here the particles that are involved, right? They move at a certain speed, right, parallel to each other. That's the definition of our longitudinal wave, with the particle motion and the wave velocity. They're typically parallel to one another. Now, when you talk about the transverse wave, the particle motion is perpendicular to the direction of the wave velocity. Okay? So keep that in mind. Light is an example of a transverse wave, while sound is an example of a longitudinal wave. Okay? So what typically sets these two apart really is their position. One is parallel in terms of the motion to the wave velocity, and the other, which is transverse, is nothing more than perpendicular to the wave velocity when it comes to the particle motion. Okay. So, and you can typically see that here being outlined. Okay, for a longitudinal wave, said before, uh, the wave velocity is typically parallel to the particles that are being displaced. Okay, so the particles are typically going in this formation. Okay, likewise, the velocity is also going in the same formation, parallel to one another. The particle displacement and the velocity, they're parallel to one another. Okay, and they give you this sinusoidal wave formation. Okay, the velocity of the wave and the displacement or the motion of the particle. Okay. On the other hand, we have a transverse wave, as we said before. The displacement of the wave, displacement of the particle is perpendicular to the velocity of that particular wave. Okay, so they're perpendicular to one another. Okay. Just like a right hand triangle, this leg is perpendicular to this leg. Okay, so you can just try to make connections using your mathematical skills to some of these definitions. Okay. Now, when we start talking about uh, some of the properties of a wave, we can describe them as follows. So, for instance, if the particle displacement is typically going up and down, we know that this is primarily a transverse wave, right? Because the particle is going up and down, and our wave, right, is along what we call it your x-axis, or you can do that as well. Okay, so here when we begin to describe components of a wave, we use a different color here. A wave has to start from an origin, which is right here. Okay, then as it moves, it crosses that equilibrium line, or that, you want to call this 0, 0 if you want to, that's fine. But as it crosses the zero line and comes back to the zero line, that's really considered to be one wavelength. Okay, or you can take it from peak, okay, to peak. That's also, so this is the peak of this wavelength, and this is another peak of this wavelength. But the peak have to typically be the same in order for this kind of formation to really work. Okay, and the amplitude is nothing more than the maximum displacement at which the particles typically they move. So this is your equilibrium position right here along the x-axis. So the distance at which it moves from the x-axis to the highest point on this curve is known as your amplitude. Okay. So again, these different parts of a wave being described here is very, very important as we continue our slides. So kind of let me know if you want me to explain a little bit more, if you understand. That would be great, but if you want me to explain a little bit more, just kind of let me know. Okay. Now, take a little further in terms of how do we tie all these different descriptions of a wave into a formula. So the frequency, okay, is nothing more than a number of cycles that occur during 1 second. Okay, so as we said earlier, our equilibrium position, that was a position axis. Now this is a time axis. Our x-axis is time. Okay, so a frequency is nothing more than how many cycles does our wave oscillate per second. Okay, so 1 hertz is equivalent to 1 cycle per second. Okay, And again, the unit of a frequency is hertz. Okay, so we can say here that our frequency, right? Okay, so we have 4 cycles, right, per second. That's what this 4 hertz means. 4, and our units of time is in the denominator. So you could also write this as 4s raised to the power 1. Okay, so this s raised to the power 1 also is equivalent to a hertz. Okay, that's the units. Okay, so we see here that 4 full wavelengths will pass in 1 second. We were told here that one wavelength starts from here and it ends here. So 4 of these would be the frequency, 4 for the frequency before hertz. So 4 full wavelengths per second. Okay. Now, period, the period denoted by t, right, is the time it takes for a wave to travel a distance of 1 wavelength. Okay. So period equals seconds per cycle, which is the inverse. Okay. So the inverse of the frequency. So in other words, your frequency and your period are inversely proportional to one another. Okay? Just like from here to here will be your period as well. Okay? So the frequency is inversely proportional to the period, just like the period is inversely proportional to the frequency. So we're moving forward, whereby we see here we have a comparison between two types of periods. Okay, we have 1/4 of a second, 1/8 of a second, and you can see typically for yourself the actual wavelength. Okay, the length of it of 1/4 a second to that of 1/8 of a second. Okay, so again, this is going to be one wavelength of light, one wavelength. I'm sorry. 2, 3, 4. Okay. So when we tie all this together, we can say that the speed at which this wave typically moves is nothing more than lambda, which is wavelength, divided by your period. Okay? This has a unit of time, this has a unit of length. Okay? So when you divide the two, you're going to get meters per second, which is the units for speed. If we go back to our either chapter 1 or chapter 2 of our textbook, we're talking about velocity. They share the same units. Okay? So as I have here, proven to you that speed is meters per second, our wavelength is a meter, the period is seconds, and frequency is hertz, which is just 1 over s. Okay. So we have here an example. I'll do this one, but I'm gonna have you do the rest though. Okay. So for sound waves with a speed of 344 meters per second and frequencies of I'm going to do A, 20 hertz, and B, 20 kilohertz. What is the wavelength of each of the sound waves? I'm going to do A. Okay, so we're given our nu, which is the speed, right, of this wave, and that is going to be 344 meters per second. Okay, and they want us to find the wavelength. They gave us the frequency. The frequency is 20 hertz, or it can be written as 21 over second. Okay. So the solution for this, we know that our nu, our velocity, happens to be lambda times the frequency. So that's going to be 344 meters per second times, times our frequency, which is 21, I'm sorry, I made a mistake here in my calculation, sorry. It has to be, we need to find out what is going to be, we need to find the wavelength, sorry, to give us the velocity. Oops. Okay, so we noticed here that nu happens to be lambda times the frequency, right? Well, when I say nu, meaning the speed of the wave. So we need to find the wavelength. So I'm going to rearrange this formula here. Lambda happens to be the velocity divided by the frequency. Okay. Oops, sorry. And now we're going to get 344 meters per second times 20, but the time, s raised to the power negative 1 equals 1 over s, right? But if I have 1 over s in the denominator, this s can now go to the numerator, which is what we have here, and then I can cross out my seconds, right? And my lambda happens to be 17.2 meters, because I only have meters left. My seconds cancel out. So this will be my answer. Okay. Sorry about that. Okay. So now we can move forward and let's go to slide 13. We have another practice problem here where the sound wave has a speed of 344 meters per second and has a wavelength of 0.5 meters. What is the frequency of the wave? And what is the period of the wave? So I'm going to just do one of these, which is going to be the frequency. I'm going to tackle that problem. I'm going to have you tackle the rest. Okay. So we have here, we're given the actual speed. Okay. And we're also given the wavelength of light. Okay. And then our solution, they want to know what is the frequency. Okay. So we know that speed happens to be lambda, which is the wavelength of the sound, right, times the frequency. So if I were to rearrange this formula where the velocity divided by the lambda is going to give me the frequency. Okay. Now the velocity happens to be 344 meters per second times 0.5 meters. The meters cancel out. Okay. And now the frequency happens to be 688 1 over second, or 688 hertz. Okay. Okay. So moving on to our light waves, and I'll have you do the period. How would you do the period? Okay. Moving on to light waves. The light wave typically belongs to what we call a family of electromagnetic waves, okay, which primarily includes a lot of the gamma rays, X-rays, what we call the visual rays of the human eye, which you can see the visible range, which is right here. Okay, you have your gamma rays, okay, ultraviolet. So this is along your electromagnetic spectrum right here, right? And along the spectrum, you have electromagnetic waves, okay? And they oscillate at various frequencies, okay, over a prescribed wavelength of light, okay? So the human eye, of course, is only going to be very sensitive to a very narrow portion of this electromagnetic spectrum, okay? Of course, if you were to shine white light through a prism, you're going to get the different colors that we see here. So keep in mind that when it comes to electromagnetic waves, there's a vibration of the electric and magnetic fields, right? And they typically oscillate perpendicular to one another in the direction at which the wave typically propagates. In this case here, the field energy is going to radiate outwardly, right, with at a speed of c, where that c is nothing more than the speed of light, and that's 3.00 times 10 to the negative 8 meters per second. Okay. Again, this is going to be the speed of light in a vacuum. Okay, so there's no interference at all while it's in vacuum. Okay, and this is typically the formation of how these waves typically oscillate perpendicular to one another along the direction of the wave propagation. Now you'll notice that when it comes to our radio wavelengths, our AM typically has a very smaller frequency compared to that of the FM. Okay? And this is typically being controlled by your wavelength of light. Okay? As your wavelength, which is denoted by the c, speed of light divided by frequency, as my frequency gets bigger, right, my wavelength has to get smaller. Okay? And you can see here how my AM wavelength is longer, right? Because if my frequency is smaller, right, for AM, my wavelength is going to be larger, or longer, I should say. Okay? So that's how you can typically just look at the equation and let it kind of give you the correlation. Okay. So you're moving forward. I would like for you to do this problem yourself. Okay. You may see something like that on your test. Also, I'd like for you to do this as well. Okay. So now moving on to our visible light. The range of our visible light typically is around 10 to the 14, okay, hertz. And the wavelength of light is typically expressed in nanometers. Okay, 1 nanometer equals 10 to the negative 9 meters. So that N is 10 to the negative 9. Okay, and the visible spectrum of visible light typically extends all the way from 400 to 700 nanometers. So we're looking from here just slightly beyond the ultraviolet all the way to the right before the infrared. Okay, this is where the visible region of light typically dwells. This region right here. Okay. So you typically the distance from the Earth to the Moon can be accurately measured by aiming a laser beam from Earth at the retroreflective mirrors left on the surface of the Moon by Apollo astronauts. Okay, so this is just another way in which light can travel from Earth to the Moon and then back to the Earth again. Okay. Another interesting wave will be our sound waves. Okay. And our sound waves typically they propagate longitudinally, right? Through various types of matters such as our solid, liquid, gas. Okay. Now this vibration can be produced by what's known as a tuning fork. Okay. Whereby it kind of produces a series of compression regions, high pressures and low pressures. So with the continual vibration, there's going to be a series of high, low pressure regions traveling, outward, forming a longitudinal wave. You can see here with this tuning fork how waves are typically being, you have a high region and you have a low region. Okay, and as you can see here at the ends of the fork, the air is typically being compressed as it propagates. The air is being compressed. When the fork moves back, it produces an area of a low pressure, which makes sense, right? So when we look at the spectrum in which sound typically has an effect, it has different regions. So for infrasonic, we know that frequency has to typically be less than 20 hertz. For it to be audible for human applications, our frequency has to be between 20 hertz and 20 kilohertz. Okay. And for ultrasonic applications, whereby this is typically used in more research applications. Um, you can use this for cleaning. You can use this to be able to remove debris from different substrates. So you can use the ultrasonic mechanism. Okay, and this also produces heat as a function of time. Okay. Okay. So when we look at this, the audible region, of course, which is dealing with human application, okay, we're here. This is our threshold. That's our maximum, and of course, this is our minimum. This is our minimum right here. Okay. When it comes to loudness and intensity, in particular, loudness can be very relative. Okay, while intensity is very quantitative and is a measure of the rate of energy transfer through a given area. Okay. So energy is typically measured power per unit area, and the threshold of hearing is 10 to the negative 12 watts per unit area. Okay, an intensity of about 1 watts per unit area is said to be very painful to the ear. So, relationship between your intensity and your radius, of course, they're inversely proportional of one another. Okay? And this kind of brings about the decibel scale, okay? How sound intensity is typically being measured. So we have here a riveting machine is at 120 decibels. Okay. We have a subway train about 90. And we have a quiet room which is about 20 decibels. Okay. So kind of keep these in mind in terms of the different decibels, because even if you are in a workplace they use a lot of machinery, you should be very, very aware of the amount of decibels those machines put out so you don't compromise your own hearing. Okay. So I'd like for you to do this particular example here too as well. Okay. So now when we start talking about ultrasound, we start talking about waves with a frequency greater than 20 kilohertz. This is 20 kilohertz, okay, which cannot be detected by the human ear. However, there are some animals that can actually detect this size of a frequency. And the reflection of the ultrasound frequency typically are used to examine parts of the body or unborn child, of course, which is very, very or less risky than using x-rays. Also, this size of when it comes to ultrasound, this size of the frequency is used in cleaning, as I said earlier, to reach and when you want to be able to clean certain types of jewelry or lab equipment, as I said earlier. Okay, you can use this type of technique, ultrasound. Again, it has a very high frequency of 20 kilohertz. It's known that bats, in particular, use reflections of ultrasound for navigation and to locate food. So when we talk about the speed of sound, we start delving into different aspects of a particular medium, right? That makes up the arena in which the sound could actually flow through. Okay, and that's very important because when it comes to the speed of sound, your medium has to possess a certain type of makeup in terms of its material, which you call a cladding. Okay, well that's particularly for light. But in this case, the medium in which the sound is going to travel, the material plays a big important role in it, right? So the speed of sound increases with increasing temperature. Okay? The speed of sound in air can be at room temperature, 344 meters per second, or at 0 degrees Celsius, 341 meters per second. Okay. So in general, the velocity of sound increases as the density of the medium increases, which makes sense, right? But now, what if your medium, as I was saying earlier, what if your medium had pores in it? Okay, what if it had pores in it, and this medium was not carefully being made? So you have holes in your medium. What would that do to the speed of the sound? Okay. So the speed of light is much faster than the speed of sound, hands down. Okay. And so in so many cases, we see something before actually we hear it. Okay. Lightning, thunder, for example. We see it before we hear it. Okay. Now going back to this speed of light, as I said earlier, you have a cladding whereby you shoot light, and light bounces off this structure here inside. So it's very, to be able to get the same intensity of light, or to keep most of it, because there's going to be some transfer of energy, you want to make sure the inside of your medium is very smooth, and it has, the surface roughness is very, very low. Okay. So a 5-second lap between seeing lightning and hearing the thunder indicates that the storm is at a distance of approximately 1 mile. Now I want you to take out some time to do your example problem as well. Okay. And I don't want to do them for you, because I do want you to get more understanding. If you get stuck, please let me know and I can help you. Okay. Here's another practice problem as well. We have another one here as well. And all these may be similar to what's going to be on your test as well. Okay. So we talk about the Doppler effect. What we're doing is we're looking at an apparent change in the frequency resulting to the relative motion of the source and the observer. So there's a relationship between the source of our frequency and the observer. Okay. As a moving sound source approaches the observer, the waves in front are bunched up, right? And the waves behind are spread out due to the movement of the sound source. In other words, the observer hears a higher pitch, meaning a shorter wavelength, as the sound approaches, right? And then hears a lower pitch as the source departs. And you can see that here in this, you can see that better here in this illustration here. Okay. So as you're approaching, you can see that the wavelength is a lot shorter, and then once passes, it gets longer. Okay. Like I said before, the wavelengths, the waves are typically bunched up, pretty much here. Higher frequency. Okay. And behind you, the waves spread out, having a lower frequency. Okay. So this kind of moves into what we know as our Doppler effect, right? And what that typically means that there's going to be a shift in your electromagnetic spectrum. Okay. So you typically want to have a blue shift, as we call it, right? When there's a shift to a shorter wavelength of light. And what that means is here, if I come back here, shorter wavelength of light. ultrasound. Okay, so here, come back to this one. So your shortest wavelength of light really starts here, and it gets longer and longer as you progress further out. Okay, so from our visible region, really going back to our left is a shorter wavelength, and going to your right is a longer wavelength. Okay, so when they say something that to the fact that there's a blue shift and you have a shorter wavelength as a light source, okay, that's what they mean. Okay. Come back here. So blue shift, a shift to shorter wavelength as a light source approaches the observer. So as a light source, so again this is our source and this is our observer. So as your light source is approaching the observer, okay, it's going to be a blue shift, okay, indicating that the wavelength of light is getting shorter. Okay. Now when it shifts to the left, okay, we call that a red shift. It's actually getting longer. Okay. So these shifts in wavelength tell the astronomer how great a deal relative movement is in space. Okay. So as this wavelength is getting shorter and shorter, the observer knows that the source is really close. Okay. So you have a blue shift and you have a red shift. Okay. And that's typically dealing with your uh, Doppler effect. And as I said earlier, um, so if a galaxy is moving towards observer on Earth, there's going to be a blue shift, right? And that moves this way, right? It moves to a shorter wavelength, moving this way. If it has a red shift or longer wavelength, it's moving to the right. Okay. So what I'm going to do here, I'm going to stop here, and I'm going to pick back up from standing waves on Wednesday. Okay. Thank you very much for your time. Thank you very much for your patience. If you have any questions, please let me know, and I'm here to help. Thank you very much.